Welcome everyone. In this demonstration I will show you how to perform a multi-state protein design in InteractiveROSETTA. This is a potentially powerful tool that will allow you to perform protein design on several protein states simultaneously. It can even be useful for doing so-called negative design. Say you have a protein that binds a target of interest, but also binds some other targets non-specifically. You could attempt to remedy that problem by performing multi-state design on all the bound states and tell Rosetta to choose a sequence that is optimal for the bound state of interest, but yet simultaneously unfavorable for the other states. Anyway, let's get started. For this demonstration, I will use the actual files provided by Rosetta for the multi-state design demo, so let's get the files. There are 3 of them. All of them are antibody-antigen structures and we will be optimizing the structure of the heavy chains. Okay, now that we have loaded all the structures, let's go to the multi-state protein design protocol over here. This panel has a lot of controls on them, but they are actually quite simple to use. If you are unfamiliar with what these letter buttons mean, then please see the fixed backbone design protocol link in the video description for more information. You may be wondering what this black terminal window is doing open over here. This is the design palette provided by the demo. So we are going to try to reproduce it in InteractiveROSETTA and need it open so we can make sure we are doing it right. This grid is where we will construct the design palette. There are 29 designable positions and all of them allow every amino acid except for cis. So let's add 29 positions to the palette. Okay, but we're not done yet. What do these numbers mean? This palette is for an abstract protein right now, so we have to tell Rosetta what these positions really are in the real protein structures we have loaded. You will see that each column is assigned one of the chains loaded in the sequence window. Look at our reference. It looks like the first abstract position is heavy chain residue 5. This reference is for all of the antibody chains. It is not necessary that the first position be 5 on all the chains. I could have set the first antibody to have residue 5, the second one have residue 10, and so on. It just happens to be the case that in this protein design the structures were such that it made sense to have the same residue position at every abstract location. Man, this is going to take a long time to fill up this palette. Well, there's a shortcut. If you select a residue in the sequence window and then right-click on an element in the grid, it will automatically fill in that residue for you. If you select multiple residues, it will fill in all valid residues in the selection into the clicked cell and the ones underneath it. So what I am going to do is select all of these columns in the sequence window and then just right-click in each of these columns in the grid to fill all the residues in very quickly. I'll do the whole thing right now to show you how easy this can be. Before we do it, we have to check the actual PDB numbers on the residues in the sequences. The numbers in our reference are PDB numbers. These labels on the sequence viewer are simply counting the absolute residue position. In these sequences, there are no missing residues and the numbering starts from 1, so it is not a problem. If it were a problem, I could click this button over here to change the grid numbering to PDB numbering. Anyway, I'll spend some time selecting everything I want. Okay, now that I have selected all the residues we will be designing, let's go over here and right-click in the first cell of the first heavy chain. And the whole column is now filled. Let's do the same thing in the second heavy chain column. Now the first residues in the selection were from the first heavy chain, which is not valid in this column, so all those residues were skipped. We also skipped all of the light chain and antigen residues from the first antibody. The first valid residue was the first selected residue on heavy chain 2, so we got all the right residues in this column as well. And last but not least, here is the third column. See how easy that was? What is the secondary res file thingamajig? This is totally optional and we won't be using it, but I will explain what it is. You can tell Rosetta to allow certain residues on certain states to be repacked that are not in the above palette. So for instance, if I wanted these first 4 residues to be repacked on the first antibody chain, I select that model from this menu, select the first 4 residues, and add them. So we get the NADAA keyword, which means repack these rotamers but do not change the amino acid. If you want the amino acid to be changed, you need to specify them up here. One thing I forgot to mention. If I wanted to redesign the first amino acid on the first chain, but did not want that to correspond with anything else, I could have left the fields for the other heavy chains blank. You do not need to have something in every column of this palette. Okay, now we have to specify states. The default settings assume that each model is its own state, which is assigned using these letters. If you want 2 models to be considered the same state, click on this letter to cycle through the states and assign them the same letter. When Rosetta designs them, all of the models in the state will be considered, but the score of the state will correspond to either the minimum or maximum score of any of the models in the state. You can specify which using these buttons. For this design, I want each model to be its own state, so I will leave the defaults alone. The last thing you have to do is specify the fitness function. Multi-state design uses a genetic algorithm to determine the solution to the multi-state design problem. Think of it like ordinary evolution. It considers many different solutions in a generation and then the offspring are subjected to natural selection. The good ones propagate to the next generation and recombine to find new solutions, and the bad ones are selected against. The fitness function defines the relationships the states have to one another to determine whether the solutions are good or not. It is a mathematical relationship between the states. The letters correspond to the scores of that state assigned previously. There are various operations you can apply. Let's get addition between 3 variables. Then I have to select these question marks and add the states here, so our fitness function is a plus b plus c. So all the states are weighted equally and we are trying to optimize all of them. If I wanted to negatively design c, I would have subtracted c instead of adding it. If I wanted b to be weighted twice as much as a, I would have multiplied b by 2. The Rosetta developers seem to have gotten a little carried away with all the operations and functions provided. If you look at this list, you probably will only really need basic arithmetic to do what you want. If somebody finds a valid biological use for the if-then-else function, you sir or mum win the internet. Before doing anything else, you should save the above setup in case we have to tweak some of this later. When you load the saved parameters, you need to have already loaded the appropriate models in the sequence window, otherwise the loader will not find the models that the information corresponds to and assume it is invalid. Now we can run multi-state design. This is a protocol that is currently only available on a server, so you need to have set that up previously. Anyway, I will get my results back in about an hour, so I will see you later. Okay, looks like the package is available. Let's download it. You end up getting the top 10 models and each top hit consists of a structure of each of the states. The file names should make it pretty obvious what each state is. Anyway, that's all there is to multi-state design in Interactive Rosetta. See you in the next video.